Welcome to Dr. Jimmy's Applied Calculus. Here we are in Chapter 6, looking at Section 3, bringing up logarithms, and then we're working with derivatives, so eventually derivatives of logarithms. Now, what are logarithms? Where did they come from? Well, it starts with looking at exponent rules. So, in the history of mathematical development, people looked at these interesting rules for exponents when we do operations on powers. So, the observation was that things like a product become something simpler as an exponent. So, what we might think of as a more complex operation, the product, is in the exponent a simpler operation, the sum. Because we also have other settings such that a power of a power also becomes a simpler exponent operation, which is a product. So, the observation was over time that, I could take all these complex things, powers, products, and turn them into essentially just sums. So, work with the exponent instead of the actual power. So that was the first motivation to come up with what we use as logarithms now, is this observation that if we turn these things into operations on exponents, we have a much simpler situation. So, for example, the idea was to take here a little oversimplified than the actual things that were being studied, but the idea was to take a number like 3 and write it as a power. At that time, usually interested in powers of 10. So instead of operations with 3, do operations with the exponent n. And so if you had another number, you would also come up with that same situation. So maybe 7. Rewrite it as what's the exponent of 10. So something like 3 times 7 would be computed as m plus m. So if we had n and m, instead of doing a product, we would do a sum. So here the product is fairly simple, but with large numbers, this could be quite an advantage. So instead of 3, maybe we had 3,286,526. And so then turning that into a sum could be much easier. So, the thing was, what would be, for instance, if we had 3 and we wanted to convert it to what's the exponent? So we have to come up with the exponent. Now, in the things that would be studied at a particular time in history, it wasn't that 10 the power, 10 to the n, or come up with the exponent for this. It had more to do with instead of 3, something like 2 billion over 100,000. That kind of ratio is what they were looking at. So instead of solving what's the exponent for a number like 3, they were actually looking like 2 large numbers divided. And then what's that exponent? So that's the historical setting. And so n was said to be the ratio number because of that setting. So the necessary exponent to come up with the proper ratio of 2 numbers. And so more strictly, it was then said to be the proportion number. We get proportions out of ratios, ratios give proportions. So, historically, the n that was necessary at some point became called the proportion number. And actually, it wasn't called proportion number, it was given in Greek as proportion, which is logos, shortened a little bit, and a number, which is a rhythm. That word, which is part of arithmetic. So, proportion number in Greek was log a rhythm. So we have logarithms for this necessary exponent in an equation like 10 to the n equals 3. So we'll go back to the non-racial looking form, but this was the idea. What's that exponent that makes that work? And then we could do everything in terms of exponents. So a big thing before computers and calculators, make all these computations simple to do by hand. Now, well, we don't need it for that purpose, but it gives us the solution to such an exponential equation. Or we have this exponential form of something. If we want the exponent, then now we have this name for it. We would call it the logarithm necessary to get 3. So the other thing, historically, they were looking at the base of the power being 10. Now, we tend to use it for different base situations. So we've added logarithm base 10 of 3. And notationally, we shortened logarithm to log and indicate the base as a subscript, and then 3. So the original 10 to the n equal 3 has an equivalent logarithmic form. So 10 to the n equal 3 is can be rephrased as n equal log base 10 of 3. So they give the same n. One is explicitly defined. Here's the exponent. The other one in exponential form. Well, there is an n that does this, but what is it? The answer is, now we have notation for that, log base 10 of 3. More generally, we have general exponential forms. So a power with a base and an exponent equal to some number, and we can convert it to an equivalent logarithmic form. Which would be the exponent n is equal to log with the base b of what would have been the answer k. So two different equations, but giving the same information. One tells us what the exponent is. The other one tells us what the power is. So we have an exponential form, logarithmic form of the same thing, with a general base b. So that defines the logarithm. And so some observations. Is that when you look at a logarithm expression, it would be the exponent of some power expression. So keep that in mind. The logarithm is that creature which would have been an exponent. Another observation, log sub b. This creature is a name in itself. It is a single, indivisible entity. Okay. So, represents one item. It can't be taken apart symbolically for mass symbols. So, you can't have L separate and then something OGB or LO and then GB. This has to be always kept completely together. It's not juxtaposition of L times 0 times G or something of that sort. The sub B has nothing to do with powers or something. This is just a single, altogether name, which you can't take apart as separate symbols. So it is just a symbol that happens to have 4 parts. Okay. The parts themselves have no meaning. There's nothing here about products because you put symbols next to each other or anything like that. So remember, a single entity not to be taken apart. So we have log base b, that's one thing. And then we have a function of k. Now, all those rules of exponents become rules of, well, logarithms are the exponents in powers. So they become rules of logarithms. So what are those rules? Well, one of the basic rules is that the product of 2 powers, what do you do to the exponents? You add them. So this is that reformulation of that. If you take the product of 2 powers, you add the exponents. And so on the one side, we have the exponents, which would be the logarithm, added. On the other side, we have a product first. Which if you divide 2 powers, so that's what I'll do here first, and then look at the exponent, that's the same as, oh, let's subtract exponents. So again, one of the exponent rules, but just writing it in terms of exponents. So difference of the exponents would have come from dividing 2 powers. And then there's a third basic rule, is that if we have a power of a power, so if A represents some power and then we do a power with that, so another exponent, the rule was that we multiply the exponents. So log base b of A is the basic exponent involving A, and then m is the other exponent, so this is the product. So these 3 rules of logarithms are just what happens to the exponents when we use powers. But also the reason at one point that logarithms were important is that it takes products, divisions, powers, and reduces them to sums, differences, and just basic products. Now, a little exercise. Is that with logarithms in expressions, sometimes they're expanded into terms. And we could combine them using logarithm rules. So something such as 2 log base 3 of 6 minus 5 log base 3 of 11. So this is expanded out into as many terms log base 3 as possible. We're going to combine them into a single logarithm term. And so I can use the one rule that this multiplier becomes an exponent 2, and the 5 becomes an exponent 5. And then this difference is a division before logarithm. So an expanded version can be combined into a single logarithm term. Or sometimes it's convenient to work the other way. You start with a combined expression. So maybe I have log base 7 of 98 over 3. So I could break that apart. First I see a division, so separate logarithms as a difference. I could continue because 98 would be 49 times 2. So I have log base 7 squared times 2 minus log base 7 of 3. So then I would have log base 7 squared plus log base 7 of 2 minus log base 7 of 3. Log base 7 of 2, log base 7 of 3. Well, really can't go any farther. We can't really break it up into nice products of whole numbers or divisions. This first one, we could continue. We could make it 2 log base 7 of 7, or observe that log base 7 squared, what is the exponent of 7? Well, it's 2. And we get a completely expanded version with simplifications when we can actually write down the exact exponent. Now, many times you'll see log without indicating a base. So log of n. And so usually we will be meaning log base 10. So a lot of times the 10 is dropped from the notation. This is called the common logarithm in many settings. Now, this is one convention. We have to be a little careful. In settings on a computer or possibly a calculator, you type things inline as text. In that situation, it might be LOG 10 instead of just LOG. So be aware that that might happen. In this course, I'm going to use log as log base 10, and it will be in many places. The other setting is ln of a number, which is another logarithm, but base e, that natural number we looked at when we did exponentials and their derivatives. So usually instead of log base e, we write ln and then of n. And this is called the natural logarithm. Now, usually in typeset form or text nicely typed out, L is distinguishable. But if I'm doing this, in this case, the L, it's a little hard to tell in handwriting. 1L, what is that creature? So, in handwriting, I usually make the L script to distinguish that that is ln. So, the natural log. Now, on a calculator, you will find that you don't have too many choices for computing logarithms. Okay? You have a choice of log, common logs, or natural logs, and they don't give you options for other bases. So let's bring in another rule that happens. If you have log with a particular base of something, so maybe log base A of something like Q, it can be converted into a different base. Part of that conversion is it's going to be log of the same quantity, but then it's changed by log of the other base. So if you wanted log base 7 of 3 and you go to your calculator, you would have to do log base 10 of 3, so same logarithm, but also divide by log base 10 of 7. Then you could compute it with your calculator. And this on a calculator comes out to approximately 0.564575. So a little conversion between bases. The same thing would be true. We could use the calculator ln. This ratio, if it's the same base, is always going to be the same number. Now, let's look at it. Go back, we had exponential functions. Okay, so logarithms come by observing things about exponents in exponentials. So if we had y equal b to the x, then the inverse relationship or graph would be from x equal b exponent y. So we interchange x and y. Now this inverts the ordered pairs, but is this result going to be a new function, or is it just a relation? Oh, well, we have observed that we can solve for y because we have the exponential form, and now the logarithmic form is the solution. So every x gives us 1y, and we have the inverse, not just reversing the coordinates and getting another graph, but an actual graph of another function. So we have the two functions. The exponential, some base with exponent x varying, and the other one is log with the same base of a variable x. And we've observed that these are inverses of each other as functions. So that means that if we do f of g of x, that would give us x, which in this case would be b with exponent g of x, which is b, exponent would be log base b of x. So that combination always gives me x. We also get that x would be g of f of x, which would be log base b, which is the g of f of x. But f of x is b to the x. This one is a straightforward, or more straightforward observation. We might not look at it as inverses, is that this is asking, what is the exponent of b? Oh, it's x. So the logarithm was constructed really to be the inverse of the exponentials. And so you can take advantage of this. B log base b of x is just x. Log base b of b to the x is just x. Let's see. Any log base b of 1 would be 0. B to the 0 is always 1. Of course, from what we just looked at, log base b of b, we might observe, is 1. Now, since we have the logarithm, is the inverse function of an exponential, then the derivatives, inverse function derivatives, are reciprocals. So the derivative of g is the reciprocal of the derivative of f, but f has to be evaluated at g of x. So in this case, we get the derivative of the log base b of x would be 1 over the derivative of f, which is, oh, that's the exponential. Exponential derivative is always the exponential with the natural log of b. But if we take b with an exponent g, which is log base b of x, we end up with just 1 over this part. Oh, that's just x. So the derivative of the logarithm is the reciprocal, and then we bring in the natural log of whatever the base is. So now we can work with derivatives of expressions that might have logarithms. If y is equal to e to the x, then the derivative, whoops, excuse me, I want to talk about logarithms. So I want natural, but not exponential. I want the natural log. So back to natural log of x. So every log, the derivative is the reciprocal. In the case of natural log, the natural log of e gives me 1. So it is exactly the reciprocal. If I have a natural log of something more than just an x, maybe 4x cubed minus 2x plus 7, and I want the derivative, this is going to be a chain rule. So it's this product. We have the outside, which is the natural log. So we're going to do its derivative and then multiply by the derivative of the inside, which is the 4x cubed minus 2x plus 7. But derivative of natural log is the reciprocal, and then we have the derivative of the inside, which is 12x squared minus 2. But it's not the reciprocal of x, it's a reciprocal of whatever we have the natural log of. In this case, 4x cubed minus 2x plus 7. And then I might combine this as a fraction, 12x squared minus 2, all divided by 4x cubed minus 2x plus 7. If we have a different base, maybe base 10, so we have y is equal to log of 5x cubed plus 7, the derivative will start out with the reciprocal. So no logarithms. So 1 over the 5x cubed plus 7, but the base isn't e, it's 10. So we'll have a natural log of 10, and then times derivative of this inside, in this case 15x squared. So derivatives of logarithms. The interesting thing is the derivative has no logarithm in it in general, other than possibly a fixed natural log of the base. Now, some more observations of the inverse relationship of exponentials and logarithms. If we took basic exponential growth, so our basic exponential y equals 3 to the x, we could do a similar thing with decay. It has characteristics, but if we look at the logarithm, log base 3 of x, it would be the inverse. So if I took a 45-degree line and then reflected the picture, let's see. A little trouble reflecting my picture. I'm sorry. And I have everything together now. So if I reflect this through 45 degrees, I have a picture of the logarithm. This may not be the best sketching, but it's the right idea. So exponential growth becomes, in the inverse, this picture of log base 3. Now, there are certain observations. We have a horizontal asymptote for the exponentials. In general, y equals 0 is that line, because 0 with the observation is the limit as x goes to minus infinity of 3 to the x. Of course, if we look at the other end, we don't get asymptotic behavior. Because 3 to the x grows without bounds, so we get an infinity at the other end. So characteristics of that, we also have in this picture that without other coefficients or terms, this would cross at 1, so this would also be at 1. And then we get the asymptotic behavior that was along the x-axis is now along a vertical. And the picture x equals 0, which would come from a limit x approaching 0, but in this case from the right side of that logarithm. Of course, there are no values for negative x or 0, so we can't take the limit, but we can look at the limit as x becomes large for logarithms, which would be infinity. That's because it would be the reflection of this exponential growth part, which would be what's going out in this y direction would have been on this picture what went in the x direction. The x direction goes forever, so this goes up. So the limit is infinite. This rises ever so slowly, but never stops rising. Eventually, it's as high as you want. It just takes a lot longer than the exponential.